Okay, hi guys. So in this lecture, we'll be continuing on seeing some more examples on the Graham's diffusion law, and we'll see some examples here. So let's say we have two gas present, and we have a tube of length L. Okay, so we have gas A at one of the corners or one of the ends of the tube, and gas B on the other end of the tube. Okay, so let's say gas A and gas B are introduced in the tube, and we have to find the length at which both of them meets. We have been given the molar mass of gas A as Ma and molar mass of gas B as Mb. Okay, so obviously the cross section area of the tube is A. Okay, and let's say gas A covers distance x and gas B covers distance L minus x, where L is the total length of the tube. Okay, so in this case we can write that volume is equals to A times L, and we can write that the rate or R1 upon R2 would be equals to root M2 upon M1, and R1 can be written as volume times length of the tube. Okay, and rate would be volume times length, volume divided by rather time which it takes to cover distance x, and R2 would be again volume for gas B. So until this point there would be gas B, and this until this point there would be gas A. Okay, so volume of the gas B or V2 divided by time, and T would be same for both of the gases. Why? Because T is the common time at which both of the gases meet at this point. Okay, so we can write that R1 upon R2 is V1 upon T, and R2 is V2 upon T, which should be equals to root of M2 upon M1. In this case M2 would be gas B and M2 would be gas A, M1 would be gas A. So here we can write that V1 would be A times what is the distance covered by V1 or gas A. It would be x divided by time T divided by V2 is volume 2 is cross sectional area divided by multiplied with length of the gas B in the tube, at meeting point. This meeting point would be L minus x divided by time T, which is the time which gas B takes to meet gas A, and this should be equals to root of Mb upon Ma. We can simplify this equation, cut out the unnecessary variables. So only thing which is remaining is x upon L minus x, would be nothing but Mb upon Ma. Once we know the value of Mb and Ma, x can be calculated in terms of L, or x can be a function of L. Okay, so with this we come to the end of this chapter. In the next chapter will be the next chapter which we will be taking on is nothing but kinetic theory of gases. Okay, so let's get started on the same, which is kinetic theory of gases. Okay, so before starting on the kinetic theory of gases, let's actually write down some of the assumptions which we are going to make before discussing any other concepts of KTG. This is also called KTG. Okay, assumptions. So the first is volume of ideal gas is considered negligible with respect to the volume of the vessel. Okay, so volume of ideal gas is negligible with respect to volume of vessel. Second is no intermolecular interaction between ideal gas molecules would be taken into account. Okay, no intermolecular interaction between molecules of ideal gas. third is all collisions are perfectly elastic and no loss in kinetic energy would be there. All collisions are considered elastic and no loss in kinetic energy happens when molecules collide with each other. Okay. Fourth point is that pressure exerted by the gas molecules due to collisions of molecules would be just taken on the sides of the container. Okay, so if we have to calculate the pressure exerted by gas molecules, then we will be taking into account the collisions of molecules on the sides of container. Okay, and when we talk about average kinetic energy of gas molecules will be, so when we talk about the average kinetic energy of the gas molecules, that quantity is directly proportional to the temperature of the gas in Kelvin. Okay, and we can write that so PV is 1 by 3 mn Vrms square. Okay, we'll be coming into the kinetic energy shortly, but before that I'm just writing this formula, which is a very important formula, where m is the mass of gas molecule. Okay, n is number of gas molecules, and Vrms is root mean square speed. Square speed. Okay, and if we write u or v square or u square, anything you can call, so which is this, so I'm just writing Vrms here and v square here, so v square is mean squared speed. Okay, so now we can write that average kinetic energy of gas molecules would be equals to half mu square. Okay, and we can write from this equation that PV equals to 2 by 3 n times half mu square. Okay, so this would be equals to PV equals to 2 by 3 n kinetic energy of molecule. Okay, so next, for 1 mole of a gas we can write that PV is 2 by 3 Na times half mu square. Okay, hence PV would be equals to 2 by 3 Na times kinetic energy of a molecule. Okay, so this is can be written as 2 by 3 kinetic energy of 1 mole of a gas. Okay, or we can write that kinetic energy of a mole is nothing but 3 by 2 times PV, which is nothing but 3 by 2 times nRT. N is 1, so 3 by 2 times RT. So kinetic energy of 1 mole of a gas is 3 by 2 times of RT. And if you have to write it down, kinetic energy of one molecule, so that would be 3 by 2 times of RT divided by Na. Why? Because kinetic energy of 1 mole would be equals to Na times kinetic energy of a molecule. So from that equation we can write that kinetic energy of a molecule would be kinetic energy of a mole, which is 3 by 2 RT divided by Na. Okay, I'm just erasing it. I just wrote it for the understanding sake. Okay, so from here we can equate half mu square with nothing but 3 by 2 kT, where I am writing R by Na as kT. Okay, and from here, from this equation we can write that kinetic energy of, let's say, n moles of a gas would be equals to 3 by 2 nRT. Okay, by the way, I mentioned a constant here, which is K. K was nothing but R upon Na. Okay, and this K is nothing but Boltzmann constant. Okay, so with this we come to the end of this lecture. In the next lecture we'll be discussing on Maxwell's distribution curve. Till then, good luck and goodbye.